Okay, what we'd like to do is kind of review some calculus, hopefully, before we kind of apply it to our physics and our motion equations. So, as just a basic review here, we have a XY axis here, and let's draw a line. So we have a line on here, and we know that over here we have the y-axis, and here we have the x-axis. And let's say I want to figure out the slope of this line. And just a review of how to figure out slope. Of course, we need 2 points to figure out the slope of a line. I need 2 points. We'll put on a couple points here. We'll say a point right here and a point right here. And we'll say that this point here is, we'll call this A, and we'll call this down here at x equals B. And then, of course, we have 2 places over here on our y also. And y has, a straight line, we know the equation for a straight line. There's a form for it, y equals mx plus b. And we could put in various x's if we know our slope and our y-intercept. We could put in various x's to figure out what y equals. And another way that we started writing this in math is instead of y, we write a function of x. So, if we put in x for this particular function right here, and we have fx equals mx plus b, and if we put in various x's in here, then we get what y equals if x is put in. So we call this y function of x. So instead of this y over here, we might have, it might be, the function of x. And so, so what is this point right here on the y-axis? Well, it'd be the function if you put in a, and this one right here would be the function if you put in b. So these 2 points here, if we look at these points, you put the x first. This would be b, comma f of b, and this one here would be a, comma f of, whoops, this one would be a, comma f of a for our other coordinate. And so if we want to find the slope, you remember, hopefully, that slope equals rise over run. And another way we can write that is change in y over change in x. And so if we subtract our y's and then divide that by subtracting our x's, and we need to subtract in the same order, so it doesn't matter whether you go subtract this way or you subtract this way. Usually we take our biggest one and subtract our smaller one, just as kind of an order of the way we do things. So what we would have is we'd have f of b minus f of a all over b minus a. That's change in y's over our change in x's. And so this is the equation for how we would find the slope if I had 2 points. It'd be really easy. For instance, if this was like 1 comma 3, and this was 5 comma 11, then we would do f of b minus f of a, so 11 minus 3 over b minus a, so it'd be 5 minus 1, and we would get 11 minus 3 is 8 over 5 minus 1 is 4, and 8 divided by 4 is 2. So the slope of this line, the steepness of this line would be 2. We could just plug these numbers in there, and we'd be able to find the slope of a straight line. Hopefully that's all review on how we would do that. It's pretty easy when you just have a straight line to figure out the slope. You just need 2 points and you can figure out the slope. And that would be, for instance, on a displacement time graph, that would be the constant velocity. At any point on this graph, all you have to do is put that equation in and you'd be able to find the slope of the line. Okay, so now let's look at something a little bit more complicated. Let's say that we have a curve. That's a pretty good curve, actually. We have a curve on here, and I want to find out how fast I'm going, or I want to figure out what is the slope of the on this curve. I want to figure out what is the slope at this point right here. Well, this causes some problems. This makes it a lot more difficult because what am I asking for? I'm actually asking for what is the slope of the line that goes through that point, and that's a tangent line to this curve. And so how do I figure out the slope of that line? Because see, a curve is the slope is constantly changing all the time, and I want to figure out what is the slope at an exact instant. At this exact point right here at this particular time, this particular x. What is the slope right there? And this is hard because I need 2 points usually for the slope of a line. So I could kind of exaggerate this a little bit, and I could say, well, what if we just pick a time or a x further down here, so something like down here, and we come up here and we put on a new point. And what if I figured out the slope of the line between those 2 points? Well, it wouldn't. I mean, maybe it'd be close, but it wouldn't be the greatest measurement for the slope of the line through that single point. If I kind of redraw this here, and let's try that again. I wonder if I can use this thing, if this will work. It's not very good. That didn't work at all. Nope, messed that up. Okay, sorry about that. Let's try it again. See, if we draw a big curve here like this, and if I'm going to kind of blow this up. So let's say I have a point here. I want to figure out what the slope is at this point right here, which would be the slope of the tangent line of this one line that goes to that point that's tangent to this curve. And I could say, well, I'll come down here a little bit further and I'll put another point, and if I draw a line between those, I draw a line between those, and I can find the slope of that because I have 2 points. That'd be easy enough to do, but the problem is this slope is probably not going to, it's going to be a very rough approximation of what the slope of the line is through this single point. And so, you can make an argument that, well, we could then, instead of going that far away, let's come down here and put a point here. Let's get a little closer to it. And that probably would be better because now I'd have a slope that's getting closer to approximating the slope of the line that's tangent to the curve at that point. But you could keep making the argument that, well, let's get a little closer. Let's go here. And then I'd have, if I found the slope of the line between those 2 points, then see, I'm getting more on the curve. I'm getting closer to this point. But really what I need is the slope of the line that is tangent to this one single point, and I only have 1 point there. So this becomes a little bit difficult here on how we should do this. Isaac Newton called these fluctuations, and this is why he invented calculus. So if we look at this again, we'll take we'll draw a curve on here again. And so what we're going to do is we're going to look at this, and we want to figure out, like, at this particular point right here, and we're going to call that point like point X. We'll call it X of naught. Put a little 0 there, X naught. And of course over here, the Y, this is the X-axis over here, and over here we have the Y-axis, or we could call it the function axis, the function of x axis. And what we're going to do here is we're going to take 2 points. We're going to take this point, x of naught, and then of course over here it would be f of x naught would be our y value. And then we want to come out here to a new point somewhere clear out here, we'll say. And if I take that down, this is going to be a certain x difference later. So we could call this x naught plus, some delta x. So it's like some change in x from here to here. Sometimes this is used. In my case right now, I'm going to use x naught plus h for Herman. So I'm going to have x naught plus a little bit more, so h distance down this x-axis. So this point right here is going to be x naught plus h. And so what would the y value be up here? Well, it'd be the function at x naught plus h. And so we can find the slope between these two. It's just rise over run. It's very easy. Slope equals rise over run, which of course is your change in y over your change in x. And if we figure that out, it would be f of, we have our 2 points right here. It'd be the difference in y's right here. It'd be f of x naught plus h minus f of x naught, that's our y's, over our x's, which would be x naught plus h, minus x naught. Here's our 2 values for our x, minus x naught. And you see I have an x naught minus an x naught, so that part actually goes away, and I have f of x naught plus h minus f of x naught all over h. And so this would be the slope if I could plug in numbers here for my x naught and how much it is for h. I'd have a slope of the line between these 2 points, but that's not exactly what I want. If you remember, I want the slope, it'd be better if I used a point here and this point, or maybe I used a point here and this point. That'd be even better. Or if I used a point here and that. Well, so what are we doing? We're taking our delta x or our h, and we're trying to make it smaller and smaller and smaller, and we're trying to get it really close to this point right here. In fact, what we're trying to do is we're trying to get h to be down to basically 0. So if we could get h down to 0, we'd actually have our 2 points would be on the same point, and then if we could figure out, how does the slope change? Now the slope over here is going to change as we make this h smaller and smaller and smaller and smaller. This slope value is obviously going to change. So what's going to be the limit to the change? I mean, how far is the slope is going to change down to what's it finally going to be limited by when we get h all the way down to 0. So the way we write that is we're taking the limit of this, as h goes towards 0. That's kind of how we write this. The limit of this thing, shouldn't have an equal sign there, limit of this thing as h goes to 0. And what this actually is called is a new function. It's a new function. It's called f prime of x naught. It's a new function. It's called the derivative, actually. So it's the derivative is actually finding the slope of a point at this tangent to the curve. And so we'd want to be able to see, what happens to this curve. If I knew this function, we could actually have a function that we would know, and we could plug in numbers here and figure out what would happen to this slope as we took h and we approached it towards a really, really, really small, or down to 0. Okay, so let's kind of relook at that then. Let's do that kind of over again. And let's say that we have a curve, and we know what the function is. Let's say we put it in here, and we have this kind of goes up on the other sides here. And we'll say this function is y equals x squared. Okay, so this function of x is equal to x squared, and we want to figure out, what the slope is at any point on here. If I am given an x value, what would be the slope at any point on here is what I would like to know. So like, right here at this point, what is the slope at that point right there? So again, we could call this x. I could call this here x naught. And we could come down here a little ways later, and we'll say this is x naught plus h. And well, what is this? Well, this is it's the function of x naught, and right here is the function of x naught plus h. And the thing is, we actually know what the function of this thing is. So the function is x squared. So the function of x naught would be x naught squared. X naught squared. So I'm gonna, if I put in my slope, if I calculate out my slope formula, which we did earlier, I have f of x naught plus h minus f of x naught all over x naught plus h minus x naught, and my x naughts of course cancel out, and so I have f of x naught plus h minus f of x naught all over h in this case. And so I know what the function of this particular curve is. It's x squared, y equals x squared. So what is the function? What does y equal if you put in x naught plus h into this function? Well, it's going to be x naught plus h squared minus, what's the function if you put x naught in it? Well, it's going to be x naught squared all over h. And if I do this out here, I'm going to get x naught squared plus 2 x naught h plus h squared minus x naught squared all over h. And you'll notice that x naught squared here and here cancel out. And I could take an h out of both of these top parts, so I end up getting 2x naught plus h. So this would be the slope. All we did was figure out the slope. That's all we did, the slope between these 2 points. That's all we did. And that would be the slope of these two. Now what I want to do though is I want to say, let's take this point here and let's bring it closer and closer and closer and closer to this point here, so that I can figure out what is the slope of the line that's right here, tangent to the curve at that particular point. Well, how do I do that? Well, I take the limit of this slope as h approaches 0. And what would that be? Well, if you take h smaller and smaller, I take this right here, h smaller and smaller and smaller until it's approaching 0, you can just plug 0 in there to see what is the limit. Where is it going to go? And you'll notice that the limit of 2x naught plus h, as h goes to 0, if I put in 0 in there, it would be 2 times x naught. It would be 2 times x naught. So it'd just be 2 times whatever your x value is. So this makes it really really easy here. Now what I've done here is I've actually taken the derivative of this function. This is called the derivative. And now if I have any value, like for instance, I want to, if I actually put actual numbers in, I want to say, okay, what's the slope of the line tangent right here at this point on the curve? And we'll say that this x value right here is like 3. Okay. Well, the y value right here, the y value is 9, right? Because I put in 3 in for x, 3 squared is 9. The y value over here would be 9. Okay? But I'm asking, what is the slope of the line that is tangent right there at that point? And that's what you would use this limit for right here. And so it's 2 times x naught. So if your x naught is 3, then the slope of this line here is going to be 2 times 3. It's going to be 6. Well, what is the slope of the line here at 4? Here's 4. Well, and there's the point. Well, it's going to be a steeper line, right? Because they have a steeper slope. Okay? So I put in 4 into my derivative. 4 times 2 is 8. I'm going to have a slope of 8. I could come right here to 0. What's the slope of the line that's tangent to the curve at that point? I think you can eyeball it and see what that is. It's no slope at all. It's 0. So if I put in 0 for my x naught, 0 times 2 is 0. The slope is 0. What if I come down here and I put in like a -1 in for my x? -1 times 2 is a -2, and I'll have a slope that's at that tangent point right there, and you'll notice that it's a negative slope. It's a negative line. So what we've done here is we've taken the derivative of this particular function, which all that means, it's just real fancy language for taking the slope. But the problem is on a curve is that you need 2 points to take a slope. And on a curve, you're only looking at the slope of a line that's tangent at 1 point on the curve. So you need to set up 2 points at a place, x naught, and a certain place later, like x naught plus h later. And you just need to see what happens to the slope of the equation. You put in your rise over run. And what happens to that equation as your h, or your delta x, gets smaller and smaller and smaller to 0? What is the limit of the slope as the h naught gets, or the h gets to 0? And then that will be the equation for the slope of the line that you need there. Okay, and I think that's probably good enough. We'll probably look at some more a simpler way to do this in the next video.